In this video, we solve this geometry puzzle step by step. We have two circles, one large one, and inside of the larger one, a smaller one. And what's important is that these two circles, they share the same center. They are concentric. Let's call the radius of the small circle R1. And the radius of the large circle, let's call it R2. In addition to these two concentric circles, we have the following specific line. Any line that is tangent to the smaller circle and that goes from one point of the large circle to the other point of the large circle. And the length of this line we will call capital C. And what the puzzle now asks from us is to relate the length of this line C to R1 and R2. The radii of these two circles. And we can intuitively imagine that if these two circles get larger or smaller, so if R1 and R2 increase or decrease, that the length of this C also increases and decreases. Now the exact relation is what is asked from us. So let's see how we approach this. If we want to find some mathematical formula that includes all three of these numbers, C, R1 and R2, we need to find some kind of figure or structure inside of our given sketch that relates them all to each other. So we need to find a figure in which all of these three lines somehow come together. And the first thing we can do is to connect the center of our two circles with the point where the line C touches our inner circle. Now, because the line C is explicitly a tangent line to the inner circle, we can say several things. First, we know that this angle will always be right angled. It is in the definition of a tangent line. And in addition, we know that this point here will be the exact middle point of our line C, meaning that this will be distance C over 2, and also this part will be distance C over 2. And of course, since this new line connects the center of our two circles with our smaller circle, it will be of length the radius. So how do we now get R2 into the picture? Well, one thing we can do is to recognize that our line C goes from this point of the outer circle to this point of the outer circle. So its endpoints lie on the outer circle. And we know that if we connect the center of the outer circle with any point along its circumference, that this will also be a line of length R2, namely simply the radius of the outer circle. And at this point, we see that we indeed made a figure, in this case a right-angled triangle, in which all of these distances occur, C over 2, R2 and R1. And because it is a right-angled triangle, we can use the Pythagorean theorem, which says that, let's see, for instance, for any right-angled triangle, we have that if we call this side A, that side B, and that side C, we have that A squared plus B squared is simply equal to C squared. And now we can apply this to the right angled triangle that we found in our structure. The long side, the hypotenuse, which is C in this case, will be the long side here, which has R2, the radius of the larger circle, as its length. Therefore, this C will become R2 squared. And then we have the two right angled angles sides A and B, which in this case will be C over 2 and R1. So we have that R2 squared is equal to R1 squared plus the square of C divided by 2. And now we see that we indeed have a formula that has all of the three variables inside of it. And what we're left now to do is to isolate this C right here and write it as a function of R2 and R1. So let's simply rewrite this equation. We can first move this R1 squared to the other side of the equality sign, which then gives R2 squared minus R1 squared. And this will be equal to the square of C divided by 2. The next step is to remove this square on the right hand side by simply taking the square root of both sides. Taking the square root on the right hand side simply removes this square around C over 2, and on the left hand side we simply get the square root of R2 squared minus R1 squared. Then to completely isolate c, we multiply both sides by 2 to get rid of this divided by 2. And our final solution becomes that c, the length of this tangent line, is equal to 2 times the square root of r2 squared, the radius of the large circle squared, minus r1 squared, the radius of the smaller circle squared. And this is the solution that we were looking for. And you can always check your solution by briefly looking at some very extreme cases. Let's for instance first look when the small circle and the large circle have the same radius. So when r2 squared is roughly equal to r1 squared. Now we see from the picture that if the smaller circle expands to the size of the larger circle, that this tangent line will shrink in size all the way up to 0, in fact, when the large circle and the small circle perfectly overlap. And this is also the case if we look at our formula. If these two are equal to each other, then the difference between them will become 0, and then the length c will also become 0. So this checks out. The second limiting case is when r2 squared, so the radius of the large circle, goes to plus infinity. And it is clear that if this circle expands all the way up to infinity, then of course the line connecting two dots on this circle will also expand all the way up to infinity. And we can see this in our formula as well. If this number becomes very, very large, then our c will also become very, very large. Of course, there is also a third limiting case, the case where r1 squared becomes larger than r2 squared. So if our smaller circle actually expands and succeeds the radius of our larger circle. And I will leave it to you to figure out what then happens and what this says about our formula that we found. If you enjoyed this puzzle, give it a thumbs up and I will see you in the next one.